Cool. So welcome back to class after the midterm. So I guess the most interesting thing to everyone is to know what details I have about the midterm. So I've handed off the Scantron thing to get marked, so that'll probably come back to me today or tomorrow, so I'll release marks probably tomorrow or this weekend. That's the plan. Now, how everyone did, I obviously don't know until I get the marks, but you know, in the spirit of this class, we talked about estimation, right? So there's like, I could get an estimate of the mark by looking at like one or two of the Scantrons. So what I did is I just randomly chose one of the Scantrons and I just manually checked, and that Scantron got perfect. So it got 100%. So that means at least one person got 100%. And like, I mean, you've learned in this class that when you have n equal to 1, that's probably not a great estimate. And if I increased n, you know, then the variance would go down. And then, but anyways, here's your sample mean estimate with one sample. It's currently 100%. But we'll see what the marks say when they all come back. Okay, so that's the midterm information. Second thing is there's these midterm evaluation surveys. So I've never done this teaching business before. So yeah, I mean, like, it would be helpful if you guys fill this thing out so I know what you think about how the course is going. I can change appropriately and stuff, and then I'll know for my own self. So yeah, what's the motivation is to help me. Okay. Other things. So here's some motivation for the class, further motivation. So you may have heard that there's this thing called the Nobel Prize, and that this year's Nobel Prize, okay, there's one in like chemistry and physics, and then I think medicine and stuff. And this year's Nobel Prize in chemistry was awarded to two people from DeepMind, this Demis and John Jumper guy. And you might remember in the first lecture I talked about this whole thing of like, oh, you can use machine learning to predict like proteins and how they fold and stuff like that. Well, turns out that these two people actually won the Nobel Prize in chemistry for using this machine learning stuff to do protein folding. So that's maybe some motivation why machine learning is cool. And even more so for like what we're going to be learning today is the Nobel Prize in physics went to this guy named Jeff Hinton. And he's like one of the famous people in machine learning and stuff. And okay, there's like foundational discoveries in machine learning and stuff. But the point is that he's kind of the guy who popularized this idea of using backpropagation for training neural networks. And all it really is just gradient descent. And today we're going to learn about using gradient descent for our nice linear functions. And it's not going to be too far off this like backpropagation stuff. You just add a couple extra layers and stuff. So it's like we're really learning what people are winning Nobel Prizes for in some sense. So that should be cool, I guess. All right, that's all the hype about machine learning. Now we start with the actual content. And I'm going to remind you a little bit of what happened before, since it's been like a week since we've discussed what happened. Okay, so all I really want to say is that we were doing this. Okay, this is where all I want to say. Okay, so we were doing this optimization business. Why were we doing optimization? Well, it's because we want to learn like a good predictor, and we said we're going to like search over all the predictors by doing this thing called optimization. Okay, and we're going to talk about how that looks in a second with these loss functions and stuff. But the only thing to remember about like the optimization basics and math background and so on about this is that if you have a function, okay, and we call these functions like g, and I tell you it's convex, okay, then you can find its minimum point, so the value like w, this w vector, that minimizes it by simply setting all of its partial derivatives to 0. And what that looked like is if you have like this two-dimensional function, then that would mean like you would get, setting at 0, you get this point here for the first w star, w1 star, and for w2 star, you'd get this. So you'd end up with this point. It gives you the minimum point of the function. How is this all related? Well, it's related to the, I'm going to show you in a second. It's related that we want to find the minimum of our loss function. Well, specifically the estimate of the loss function. Okay, so all you really need to remember about like the math tools and stuff is you're going to have some function, you take its derivative and set it to 0. Okay, that's like all that really was communicated with everything before. Okay, then we finally went back to our actual machine learning setting, and I tried to explain to you how this function is related to our loss function. Okay, so then I reminded you the setting. So what is our setting? And I'm going to choose a very like specific setting because it's kind of like the simplest one to work with. And this setting is going to be this linear regression setting. So the regression part is because we have labels that are the real numbers. Okay. And that's the regression part. Then we always have features that are in RD, and I said now we're going to always consider them to be in RD plus 1, and I'm going to mention the plus 1 thing in a second. Okay, then we have this thing called our function class that we're going to consider. These are all the predictors we're going to consider. And we defined that, which I will mention in a second as well, and we had a data set. Okay, and this data set, what we use the data set for is we use it to define this thing called an estimate of the expected loss. So this L hat thing is just a function, and in this function we use the elements of the data set in this way. We like plug it into the predictor, and then there's this Y, which is the label, and then plug that all into the loss, which tells us how close our predictor is to the label, and then sum that all up. But anyways, the point is this thing's just a function. Okay. And as input, it takes, it's a function of this data set stuff, and it's a function of the predictor. And here we just like are really going to care about the predictor, so we emphasize the input is just the predictor. Okay. And our goal, right, in this whole like empirical risk minimization stuff is we want to find a good predictor. And the way we do that is we search for the argmin f. So this is using our optimization notation. We look for the argmin predictor in our set of predictors, or function class, that minimizes this estimate of the expected loss. Okay, and I said this should look very similar to what we've been looking at in optimization, which is that we have some function, and we want to find the argument that achieves the minimum of the function. And the only thing that really looks different here is the fact that we're searching over functions and not like vectors in RD or something. And so then to solve this problem, we do a couple steps, which is first we define the function class in a special way. Okay, and the way we define this function class is to be, this is like your typical thing you've seen. So they're obviously functions from x to y. I can even make this more, okay. From x to y here, remember, this thing is r to the d plus 1. This thing is just r. Okay. So these are your predictors. And they have the special property, which is all of them have what we call, they all look like linear functions, which means that they are a dot product. So the features are dot producted with some, what we call a weight vector or a parameter vector, w. Okay. So that's what the functions all look like. And this form of the functions is going to be very helpful for us to do optimization. Okay. And before we do that, I'm just going to remind you where this plus 1 business came from. So I said that like, okay, technically we're going to start, I started with saying the functions look like this, which is just like dot product times some bias term. And like, what I maybe missed is like a picture of why this would be useful. And so like when you look at this, I give you a very small picture, which is like if you try to graph a line, right? So suppose that in this case, W was just an element of R. So it's just like a value. Then you might have seen, then this, what does this equation look like? Then this equation looks something like x times W plus B, right? Which is just the equation of a line. And what does the B tell you? The B just tells you the intercept point. So this would be B. So anyways, the point of the B, the bias thing, is that it allows you to shift your linear function like up and down. Okay, that's all that the B thing is there. And then I said for mathematical convenience, we're going to group the B as one of the like weights, because then we can just describe the whole thing as a dot product. And what that meant is we take this B, we call it W naught, and then we multiply it by X naught, and we say X naught is always 1. And then you get something like this. And then we're always just going to assume from now on that our X's have X naught equal to 1. And yeah, like in the data set stuff, and our W's are always going to be like W naught to WD. Okay, so like maybe I can write that too. Which is that the W's are always going to look like this. Okay. Also an RD plus 1. And this thing is like the bias thing that tells you how much we shift the line or the plane or the hyperplane or whatever up and down. Okay, now let's get back to the objective, which is, okay, like we notice one thing before we can talk about this optimization objective, which is everything in this function class, right, has a certain form. So in particular, the thing that our learner is going to output, which is going to be f hat, right? Okay. This f hat thing is the minimizer. That thing also has this special form where it looks like this. Okay, and I'm going to say like it looks like this for a special w vector hat. This is like the w that achieves this f hat thing. So hopefully everyone can agree that the form of f hat is going to be is going to look like this. And the form of everything in this function class is going to look like this. So to find the best function, all you really need to do is search over the w's. Okay, so this is like a very key point. By defining the function class, right, in this way, that every function is in a sense characterized by the parameter vector w, searching through the function class is equivalent to searching through all the parameters. And why is that so beautiful? Well, it's because these w's are in RD plus 1, and this now just looks like a multivariate optimization problem. Okay. In particular, so these functions in here all have this form. So now we can think about searching through this function class as just searching through all the w's in this RD plus 1 space, right? To minimize our estimate of the loss, expected loss, where I've just slightly abused notation, and here I've passed in this w here, and that definition is just like, instead of plugging in f, plug in this linear expression with w in there. Okay. So now this becomes our new objective. And this should look very familiar in the sense that if you just think of this L hat as G from before, and you think of this thing as our like domain that we're searching over, then we have exactly the problem that we had before. Okay. And now we're going to work on just taking the derivatives and setting it to 0, basically, and then we get the answer. And before that, I answer some questions, which is, what does w not or b mean? How is it changing the learner function? And why is x not equal to 1? And yeah, and it's, I don't know if this plot explained things, but it's exactly that if you didn't have this b in one dimension, right, then you would only be able to draw lines like this that go through the origin. Okay, this is without b. So I don't know, like, this is without b, which is the same thing as w naught. I just like started with b to make it, to visually see that it's separate, but after that I just say that, okay, we call b w naught and call x naught 1. So really, the bias is just to be able to shift your line in one dimension or your plane in 2 dimension, or in general, it's called a hyperplane when you have multiple dimensions. So you can just shift them up and down along the axis of which the values are taken. That's all. And then x naught is just always set to 1 because this thing is just the one that multiplies exactly the bias term. Okay, so like when you do the dot product, what you want is you want to get this thing equal to 1, because then it looks the same as this b. Okay, so this is just like the, and why did we do all this is because like mathematically, then everything always just looks like dot products like this. So you don't have this plus b all the time. You could have just had this plus b and separately solved for all these variables. It's just like the math becomes, it's just annoying having the 2 cases. So we do this. Okay. Great. So we got to here. And as I said, now everything looks like we've seen before. And we want to take the derivative and set it to 0, but we need one more special property, which is that we need this thing to be convex. Okay. And it turns out that if, okay, so not even if, like, I'm just going to tell you. So we're going to pick, so we need to pick the loss, like, okay, so this thing's a function of this little L guy, right? This loss function. We haven't chosen it yet. And depending on what you choose is going to make it convex or not. Okay, like it's either going to be convex or not. It turns out if I pick L to be the squared loss, okay, you remember the squared, I'll write it in a second. Well, then you get this wonderful property, which is L hat of W is convex. Okay, so now we're in great shape. We have everything that we wanted before, which is that our function is convex, and now we just need to take its derivative and set it to 0. And then we get the parameters W, and then I'll explain to you how, at the end of the day, we get a learner that takes in a data set and outputs a function. I'll write that equation at the very end when we finish all this. Yeah. Yeah, so okay, let's just, so the story is, I think we all are on the same page that we have this estimate of the expected loss, which is L hat, and all we want to do is find the predictor F in the set of all predictors that makes this expected or estimate the smallest possible. And then we're going to output that and just call it F hat, right? The reason I call it F hat is just so I have a symbol to say this is the output. And you might notice, like, okay, here, this is actually a good point, which is like, maybe why did I use hat? Why use F hat instead of F star? Like, I've been using star for the solution to all my optimization before. Why am I using hat and why am I using W hat here? And the answer is you'll see in a couple of weeks, because we're going to use star for something else. And that's going to, like, so I didn't want the notation to clash. And that star is going to be, okay, what's that star going to be? The F star is going to be the solution to this argument when you don't have a hat. Okay, so when you remove the hat, so it's going to be the true, like the true best predictor with respect to the true expected loss. Here, this is the best predictor with respect to our estimate of it, okay? So I could have technically, like, I didn't want to overload the notation, but I could have wrote something like this, which is like, this is like F star of, and then the hat would represent the estimate of it. But I'm not going to do that because it's going to be annoying to carry it around everywhere. Okay, just a notational remark. So back to the story, which is that F hat is the solution to this thing. And then all I said is that, okay, F hat, since it's coming from this set of functions, it must take the form the following. And then I just called the specific W that achieves this like F hat, because like I just gave it a special symbol, which is W hat. I could have just as easily wrote W, but I've given it a symbol, which means it's this W hat is the W that represents this F hat function. Okay. And so then, like, it turns out that finding the F hat is the same thing as searching over all the little W's and outputting the one that minimizes this expression, because this expression is exactly the expression above with F plugged in as X dot producted with W. And so, yeah, so this like W hat that you output, if you then write your function like this, it gives you F hat. Hopefully that explains things. So it does not give you this. So this thing outputs a function. This thing outputs a W hat. But if you then take your W hat and write a function in this form, which is write your function as X transpose W, then you get F hat. And once again, the reason this F hat is the same as this F hat is because it's minimizing the same, like this thing that you're trying to minimize, right? If you plug in F as this dot product thing, what do you get? You get the following expression, which is exactly what this thing is. So the function is the same that you're minimizing. The only thing is, like, now I've made this explicit choice, which is F looks like this. Okay. So L hat of W is the same as this. The only difference is now the parameter, like the thing that's being passed as input, is not functions, but W's, okay? But as we talked about, like, it turns out that in this special function class, you can think of every single function in it having a corresponding W. So every W gives you a function, and every function has like a W representing it. So if you just find the minimum W, you can then use that W to write a function of this form, and then you get the same, there's a one-to-one like relationship with this. You can write this like much more formally, but like hopefully the intuition comes across, which is like basically every single function in here has this form. And the important thing is that because of this form, you can think that there's, for every parameter vector like W, there's a function, and for every function in your function class, there's a parameter vector. There's like a one-to-one relationship. So talking about searching over functions is the same as talking about searching over parameters. And this is like maybe one of the most important things to notice, because at the end of the day, we care about searching over functions. But this is complicated. So what we do is we say every function has an associated parameter. And here it's like, this parameter is W. We could write a more complicated function, and that's what neural networks are. They also have like parameters that describe them. And then like the way you search over neural networks, just like here, is like you then say you find the best parameters. So you search over parameters because there's a one-to-one map between your functions and the parameters that describe them. And this is really important to know, because like from now on, we're always going to be doing optimization over parameters, but you should always remember the functions. You can always write them in terms of the parameters in this way. And I'll make this more explicit, like how the actual learner function looks once we finish this calculation, and you'll see. Okay, shall we do this? So what do we have to do in particular? So what we have to do is we have to now solve for W hat. And I kind of got you guys to do something similar to this in one of the assignments, maybe two of the assignments, and so we're going to do it again. And so all that means is that we're going to take this guy, we're going to take its derivative and set it to 0. That's it. Okay. And before doing that, I'm going to do like a couple steps to make things way more explicit maybe for the first time around, and then later on in the course, I'm not going to do all these like steps of taking the derivatives and so on. Okay, so first of all, what is this thing? Well, this expression, if you remember, is like 1 over n times the sum from 1 to n of what? Well, remember, we have the squared loss, and the squared loss is our function, and the function looks like this linear expression, right? This is our function. Minus y, okay, so for the data points, squared. So this squared part is the squared loss. This thing is like the function being plugged in, okay. The definition. Great. And now we want to take the derivative with respect to each component of w. And to make this very explicit, like, what does this function look like? I write the whole thing out, and we do the derivative this way. Okay. So what that means is, like, I expand this sum so that you can clearly see what's going on in there. So when I expand the sum, it looks like this. It looks like x1 right, this is just the definition of the sum. There's n terms. Great. So now this is a bit more explicit. You don't have this weird summation notation. But we're going to want the derivatives of each individual w component. Right? This thing has d plus 1 like components, indices, dimensions, whatever. So I also write that out explicitly just to really drive the point home. So each one of these things inside, what does it look like? It looks like the dot product of, like when I expand the dot product, it's going to look like the following. Okay, maybe I remind you why it looks like this. Which is, remember that each one of these xi's, it looks like the following. It looks like xi0, which is equal to 1. And then there's xi1 all the way up to xin, oh, not n, d plus 1 indices. And this w vector looks like w naught, transpose, w1, wd. Okay, so this is what this guy looks like. Now I'm just going to plug this in and then expand the dot product. So what we get is x1, 0 times w0 plus x1, 1 times w1 all the way up to x1d times wd. Oh, and then we subtract y1. And then we square the whole thing. Okay, so that's this first term. And then we have n of these terms. Okay, so then I'm going to do like plus dot dot dot, and then I write the nth term here. Okay, so the reason I did this all very explicitly, just to like make it very clear what it means when we say we're going to take the derivative of like w0 or w1 and so on. You can just, like, when you expand it this way, you can very clearly see where does w0 participate in this equation. Okay, it's going to be like in all these n sums in here, and we forgot to square this thing, and so on. Okay. Before I take this question, I'm going to write it out in one more like simplified form, which is I'm going to write it in the following form. I'm going to take every one of these terms and I'm going to give them like this nice representation or label, which is going to be L1 hat. Okay, and this thing is going to be a function of W. Okay, and what these objects are, and they'll make the derivative easier, is that I've defined L hat I of W as simply one of these terms. So it's equal to xi transpose w vector minus yi squared. Yeah. Yeah, so the question is like all these x's and y's are coming from the one single data set, and the answer is yes. So we assume this thing is just fixed beforehand. And for that reason, like you can see that this function kind of depends on these x and y's, but we're gonna like, technically I should be writing that this depends on the data set and stuff in here, but it's just fixed always. It's always this x and y, so I don't want to jumble up all the notation and stuff. And so like it's always gonna be talking about the x and y's from this data set. And so when I expand all this stuff, this is like the first feature and all of its corresponding components. Could be something like number of rooms, age of the house, and this would be like the price, and then this would be a different house and same number of rooms and so on. Oh, and we missed the y completely here. So clearly there's a minus yn part here. Okay. Yeah, so just coming from the data set. Okay, so here's our nice, like all we've done so far is we haven't even taken a derivative. We've just expressed L hat in all sorts of different ways to kind of understand this object. So when we get to taking the derivative, it's hopefully much simpler. Okay, at this point we can take the derivative. So what we care about is the derivative of L hat with respect to each of these wj's, like each one of the dimensions of w. So I'm going to call this thing wj, and we're going to care about this for every single j from like 0 to d. And I'm going to just not write that. Okay. So what does that look like? Well, this is our expression of L hat. So it's going to look like this. If you remember, with derivatives, I can take the derivative. If I have a sum of things, the derivative of the sum is the sum. Is the sum of each one of the terms, the derivative of each one of the terms. So what I mean by that is that this is the partial derivative of L hat of 1 with respect to wj of wj. And here it's wj. And all the way up to the derivative of L hat of n with respect to wj. And this is a function of wj. Okay. That's the derivative. So all we have to do is take the so all that's left is to take the derivative of this object with respect to wj. And yeah, we know what this object is. Like I explicitly write it one more time. So this thing is like xi0 w0 plus xi1 w1 all the way up to xi d wd minus y of d, or y of n, y of I, all squared. Okay. So all we have to do is take the derivative of this object with respect to wj. So let's do that derivative. And to do that, okay, I'm going to write that derivative in here. So this is what we care about. This is like our side step here. Okay, so we're going to look at each one of these li's now, right? I representing this index. And we're going to take that derivative in terms of wj. And we're going to break that up into two steps using the chain rule, because this thing is like, it has a squared function, and then inside it has its corresponding function. Okay. And I'm going to write it like this, which is the derivative of a g function with respect to u. You might remember this. And in particular, it's going to be with respect to ui. And then you're going to have ui, and I'll define these things in 1 second, wj. So this should look very similar to this chain rule thing you've seen before. Okay. And I'm doing all these steps explicitly just so it's very clear what happened. Okay. And then finally, like, what are these functions and stuff? Well, the functions look like this, which is L hat of I of W, right? That's this thing. I'm going to call this thing G of U I equal to UI squared. And then I'm going to call UI this XI vector transpose W minus yi. Okay, all I've done is I've looked at this function, and I said this is u, and this function is just u squared, right? U squared. Okay, and the I just indicates that I'm using xi and y. Okay, all that to use this chain rule. I suspect, given you've had practice with all this, you've already worked this out in much quicker ways, and you don't have to write out all these steps. But once again, this is the explicit way. So okay, so what's the derivative of this thing? Well, the derivative of g with respect to u is 2 times ui, and then the derivative of ui with respect to wj. Okay, to get that derivative, let's recall what ui looks like. It looks like this. Explicitly, when you expand it, it looks like this. And I want the derivative with respect to wj. And if I look, wj is just going to be one of the, like for instance, if j was 1, it would just be this. This is the only place where w1 appears. Everywhere else, it's a different w index. So all those are constants, and the derivative of all those is just 0. So all you have is the derivative of one of these terms. So if j is equal to 1, it would be the derivative of this. What would that be? That would be just xi1. And in this case, it's going to be xij. Okay. That's his derivative. And in particular, I'm going to just switch these around and plug in what ui is to get 2. And the reason I'm switching this around is just for like representation coming up in a second. It'll make things look nicer. Okay, and then I plug in what this is. Right? Okay, so that's the derivative of each one of these terms. And now finally we cared about this thing. So that whole derivative, well, we know what the derivative of each one of the terms is, so now I can write out the whole thing. So now this like equal sign is going to continue with the black one from above, and what we have is something like 1 over n. And then the derivative of the first thing is 2, and now it's not xi, it's x1j times x1 dot producted with w minus y1. Okay? And you're going to notice that all of these have a 2 in the front, so I'm just going to move the 2 all the way out here. Okay. And then finally, we have xnj times xn w yn. Okay. That's it. We have the derivative now. And it turns out like you can write this in a slightly more compact way with the summation notation, and you would get the following, which is, notice how there's n of these terms. So we use the sum from I to n of xij xi dot producted with w minus yi. Okay, beautiful. So this is our derivative. You could have done like, without expanding all these terms and stuff like that, you could have just very well looked at this thing, notice that, oh, the derivative is going to, like the derivative is linear in the sense that like the derivative of a sum of things is just going to be the sum of the derivatives. Then you just take the derivative of this object in here, and then you're done, and you would have just got to there, and it would have been only a couple steps. But I once again write all this out to make it very explicit. You will very likely not want to do this when you actually work things out after a couple like tries yourself. Okay, we're done. All we need to do now is just set this derivative to 0, and we've got our answer. So let's do that. So what we got is that derivative of L hat with respect to one of the wj's, right? This is only for one of the wj's. This is for one of the wj's. It's a function of wj. Well, what is that? That's equal to, okay, we had this thing. Okay. I just copy it. And what we want to do is we want to set it to 0. Now we just have to solve this. And okay, like let's solve this thing. So first of all, I can rewrite this sum into 2 parts to make it a little bit more clear. So I'm just going to expand out the minus here. okay, minus what? Well, 2n right? That's what I have, and I need this thing equal to 0. Oh, I say implies. So I need this thing equal to 0. Now I can just move one thing to the right-hand side. And so I get 2n okay. So this is our solution. That we have. And okay, they both have 2 and n on both sides, right? So like these 2's and n's cancel out, so we can erase that. Okay, so this is actually the expression we care about, so we have this. Okay, so where did we get to? We were trying to solve for w. We got to this expression. Do we have a solution for w? So it might be a bit confusing how we get to this w. So like, what does this solution tell us and whatever? Well, first of all, recall that this is only the derivative for one of the j's, for wj, right? And if we want the value of w, right, we need to set the derivative for every single j from like 0 to d to 0. Okay. So in particular, okay, so what I mean by this is that we have this expression for all j, element of 0, 1. And to make this even more explicit, what we really have is a system of d plus 1 equations, right? So we have d plus 1 equations, and we need to solve them. What do those d plus 1 equations look like? So I write them for you because this visual turns out to be helpful. So we have these d plus 1 equations, which is like for w equal to w0 here, w1, w2, all these have to be equal to 0. So what do these equations look like? Well, they look like this. So I plug in xi, and then here, this is w. This is the 0th version, and here it's 0. Okay. And then I have this ... up to . Okay. So what I have here is there's d plus 1 equations that need to be equal. These look kind of complicated and stuff, and like if you expand them and solve them and rearrange, and then you can solve for w, right? The thing we want to solve is for w. Turns out here, linear algebra can help us a lot. This looks like something you have seen many times in linear algebra if you took linear algebra. If you didn't, I just tell you the equations. You can, when you implement these things, there's always libraries that do this for you and stuff. So, okay, what does this look like? This actually turns out you can write this in a vector and matrix form. Okay. And in particular, notice that like here you have xi index 0, and then it would be index 1 and index whatever up to d. So you can think of this guy as just a vector. And this thing is just a number, right? So what I mean by that is I can write this whole thing as the following, replacing xi with all these indices as just a vector. And I get the following expression. And then the right-hand side, similar story. I can just replace this once again, like vector times a constant, or sorry, number times a constant. I can replace the whole thing as just a vector. Okay, so now I have that the following vector has to equal to the following vector. Okay, great. Turns out, okay, so like, yeah, I need to get two vectors equal, but what you can do is you can notice that, okay, there's this thing, this expression here, and this expression here turns out to have like a special name, and you can like, in linear algebra stuff, you can write this term as one thing, or you can talk about working with this term and so on. So this thing has a special name. It's called an outer product. And in the notes, I define what this what it means to. It's the opposite of a dot product, kind of like a dot product takes two vectors and gives you a number. An outer product takes two vectors and gives you a matrix. Okay, that's all I want to say. Like, Yeah, like in the notes, I show mathematically what the object looks like. When you end up implementing these things, you don't actually end up needing to know all the steps. You just write it in code and stuff. Okay, so I'm going to call this object equal to some matrix A. Turns out to give me a matrix. Oh, sorry, not this object. So I'm going to define A now to be equal to the sum from I equal 1 to n of this guy. And notice how like this thing doesn't even depend on I. It's just a vector. You can like take it outside of the sum or anything. So I get this expression now looks like A times W vector. Right? All I've done is I've just given this object a name. Okay, it's just a computation. You can do that. This thing on the right, I'm going to give it the label of B. And it's a vector. And B is just exactly this object. Okay, so we started with something that was a vector. This thing on the left was also a vector. We still end up with something that's a vector, right? Because it's a matrix times a vector. That gives you a vector. So you get this expression. And this is like a classic expression you have in linear algebra, which is you have some matrix on the left. You're trying to solve for some vector multiplying the matrix, and you have some values that it gives you. The solution to this is like a classic result in linear algebra, which is W, the W vector just equals to the inverse of A times this B vector. Okay. And this happens if like this A, so sometimes the inverse doesn't exist. So if it exists, this is the solution. Otherwise, like we're not going to worry about it. And all I wanted to say was that this object is called the inverse of A. Okay, so I suppose that everything was looking pretty good up to this point, and then we got into some linear algebra. And then there's some new notation and stuff, which I don't think is worth going into all the details and stuff, but like all you really need to know is that to solve for W, okay, and this what is this object? This object really is at the end, like this is W hat that we were trying to solve for. Okay, so we've gotten W hat. This is the solution to this problem. Why is the solution? Because we knew this thing was convex. So what we did is we took the derivative, set it to 0 for every like index of the W vector, and then we got this answer. Okay. So when you when you implement this on a computer and stuff, you just like you'll see you just like express this thing. You can like write it out, and then you just say take inverse by using a library, and then you get the equation, and you solve. So it's like a couple lines of code, and I'll do the pseudocode in a second. And yeah, so that's the solution to this thing. So the next thing I'm going to do is write how this actually relates to our, like, I'm going to answer this question, and then I'll write the question first. So like at the end of the day, we wanted a learner. So what is the learner? And this turns out to be very easy to write now. And yeah. So before I answer this question, I answer some more questions online. So f hat is a function that minimizes the loss function. So yes, so f hat is this. I mean, it's this. It's the thing that minimizes the estimate of the expected loss. And someone asked, what exactly are the parameters in this case? And the parameters are so first you have to define your function class. And when you define your function class, depending on your definition, sometimes, like for instance, when we define it in this way, your functions have some special form, and you notice that every function in the function class has a corresponding like W, like right? This is all the functions that are of this form, which means that like every single function in here has a corresponding W that kind of describes it. We call that W the parameter, or the weights, it turns out, in machine learning. These are just the things that kind of describe each function in your function class. And is the data set for the learner and some features for the predictor? So no, like the data set, so the data set is something about like, is it split between the learner and the predictor or something? It's just like, it's all going to be used by the learner to produce a predictor. So, and I'm going to define in a second. The learner, what's the learner going to do? The learner is going to exactly solve this problem. And then it's going to output this function. And then this is a function which takes in any new feature can output a prediction for you. Nothing to do with the data set afterwards. So only the learner is using the data set. The predictor is just a function that gets output. Has nothing like, I mean, it's related to the data set based on the fact that the learner outputted it using the data set, but the predictor is just a function. Yeah. And then as the function is continuous, why are we not doing integration? That I am not sure what you mean. We never did integration to do optimization to begin with. If the function is continuous, we always took derivatives and set it to 0. Okay. So let's define the learner. And you should see how like maybe beautiful and simple and stuff it is now. It's just like, so what's the story? The story is we had, I repeat, like we had this data set. It was just like this. This is what we started with. Right, we had this data set, which was from this space, whatever. So here's the learner. The learner is a function that takes in a data set like this, right? And it has to output something, okay, like it's going to output a predictor. And since we chose our like function class to be this f thing, it's going to output this f hat from here, like clearly, right? This is the set of things it's going to output from. We kind of like fix that idea. And then the question just is like, what is this thing? Well, this thing is equal to, okay, equals to a function f hat, like this is a function. So notice here, x is just some feature in this thing. It's not from the data set, like it's just some arbitrary feature. So this is a function of features. And what is this thing? This thing is just that feature transposed times w hat. And this is the only thing that the learner really needs to do, is it needs to solve this linear algebra problem, which is that w hat equals to A inverse B vector. Okay, and where was the data set used? So this is the part that depends on D. Okay, so this is a kind of a monumental point. This is the first time we've ever actually defined the learner, and we can finally see what does it look like. And you've had this on your midterm and like on assignments before. So like this is a function that takes in a data set and it outputs a predictor function, right? Okay, like let's look at the predictor function. This thing is a function from arbitrary features, like features, right, to numbers. This dot product gives you a number. Okay, so it's just a function, and the way you decide this function, which is what the learner is doing. The learner is deciding the function I've had. How does it do it? It uses the data set through this operation. So it uses the data set, solves this problem. This gives a vector, and it just says, okay, this is my w hat. Now I output f hat to be just this dot product. Okay, so it takes a data set, solves this, outputs this. This is like a thing. Okay, maybe to make this very like much, I hope this other way of thinking about it clarifies things. Because like I guess this is like computer science and stuff. So like you guys usually see algorithms and things like this. And what is an algorithm? But like it is really just a function, right? An algorithm has some inputs, right? It takes in arguments. This is going to be the argument to the algorithm, and I'll write in a second. And then the function, like, okay, sometimes it does an operation or it outputs something. In this case, it's going to output something. What is it going to output? It's going to output f hat. So in code, you're going to, roughly speaking, this is going to be like the pseudocode. And this is what you're going to do in the next assignment, which is you're going to implement this for sure. So here's our algorithm. Okay, and this thing is going to be called, okay, so this kind of expression where you have for like the minimizer of something is called a closed form solution. So this thing, I give it like a very explicit name, which is called the closed form. Okay, and we're doing regression, right? And since our function class is these linear functions, this would be called the closed form linear regression. And what is this function? It's the learner. Okay, so it's the closed form linear regression learner. Beautiful. And so this is how you would see this thing in code. So first I have to specify the inputs to our function. Well, the inputs are just going to be a data set. Okay, and I copy this thing. Now, the way you choose to represent it on your computer and stuff, that'll be discussed in the actual assignment and stuff, but like, you're going to choose to use a matrix for these kind of things and stuff, but like for pseudocode, this is fine. So you have some data set. Then what you do is you do the mathematical operation to set A. So A just becomes this sum I equal 1 to n of xi transpose. Okay. And like probably on your computer, you're going to implement this with like a for loop. You loop over all I to n and then just do this step. Then you set this new variable A. Then you're going to set another variable B, right? So what's B going to be? Well, it's just the definition of B, which is xi vector times yi. Once again, you're probably just going to loop over and do this. And then like you're going to define a new variable called like w hat, let's say vector. And this thing is going to take the value of A inverse B. And once again, this would be like just a function from some library, which I will tell you in the assignments, which would be like numpy.inverse or whatever, A and then times B. And this would be like a dot product or, well, it's going to be a matrix vector multiplication. And so like this is how you're going to implement on the computer. And then finally, you're going to output something, which is the predictor. This is like what your learner did. It outputs a predictor. So that predictor is going to be f hat of x. And right in Python, like we're going to be able, you can output functions, and like doing this output is going to be more than just like writing this line, but you'll once again see this in the assignment. This is just pseudocode, and so you'll output this. So you'll return this. Okay, so like we have our first pseudocode, our first learner, and like in machine learning, okay, in machine learning, this thing that we've output is sometimes called, well, it's more often called a model. So so this is like, yeah, like you've taken a data set, you've done some processing on it here. This is what you've done with the data set, and you output a predictor. And now you can take this thing you outputted, and you can like take in any new feature, any new house information, and you can predict prices using it. And what you would do is you like, once again, it just takes in the new house information, multiplies it by this like fixed thing you just learned, and it produces a new price. And so like, okay, like for ChatGPT and stuff, this is what the people, oh, that's a great spelling of algorithm. Let's fix that. Algorithm. Okay. Yeah, in ChatGPT, so this is like what all the engineers worked on is like, or like the whole company is just like this part of the code. They worked really hard on the code. Okay, their code is much longer than these like 6 lines or whatever I have. But they took in some data, which was like this is their whole internet data. They did a lot of operations, which are not just like these couple matrix things. And then they outputted ChatGPT, and then you're using this output, right? They outputted this function, and then that's what you're using. And then you can take in any new text, just like here, you could take in any new feature, and you can produce corresponding responses. And that new text, that prompts you put, don't have to be prompts that ChatGPT that was trained on from the internet. It can be completely new information. So this, once again, is just any new feature unrelated to anything in the data set. Okay, that's all I have to say about this stuff. This is like beautiful. If we could just always have these nice, like that's what we're getting into next, which is like, wouldn't it be great if we could just always solve this like mathematical problem, which is like you take the derivative, set it to 0, and you're done. And it turns out sometimes you can't, sometimes you can, and sometimes you can't. And what we're going to next, which is called gradient descent, is kind of addressing the problem of when you can't always get this beautiful closed form solution type of thing. Okay, is there any questions before we jump into the next part? Yeah. Oh, this good math here? Yeah. Yeah, so the main point is that like people want, okay, so you could have just done all this stuff with like a bunch of, okay, like, I mean, you could technically write all these out on like a piece of paper and expand all this and then solve for W1 and do all this. The reason to do this is that you get like this matrix equation, and in linear algebra, we have like nice, simple ways to solve problems like this, which is like the following. Like there's like well-defined ways that you can just solve this type of it's called like a linear system of equations. So yeah, whenever you get like a system of equations like this, usually you want to make it look in this form, because then you can just use exactly this linear algebra technique to solve for it. This? Yeah. Yeah, I'm just like, throughout I've used W, so we get the solution for W. And remember the solution for W, like we call that solution the symbol W hat. So this is just like this is just a definition. Just like W hat is what we've been calling W throughout this whole thing. That's it. Like we've done this throughout, like you just kept W, you set it, and then at the end you're like, oh, W star was equal to this. And once again, here we're using hat because later on we're going to end up using star for something slightly different, so I just don't want to mix up the notation. But this W hat is exactly like the W stars we were doing here. Like it's exactly like this guy here. And it's exactly this step. Like notice here, we took the derivative, set it to 0, we just had W1, and then we're like, oh, okay. We're going to call W1 star now, this thing. Okay. So yeah, so like we've gone, this is their first implementation in code. It's going to be this. There's going to be more things you get to implement because that's what next things are all going to be algorithms kind of things. Okay, shall we go into the next part, which is all about gradient descent. So this is like the mini version of what the Jeff Hinton Nobel Prize thing kind of was related to. Okay. And I put a couple like plots and stuff to make things faster here. So yeah, this is the question, right? It's, as I mentioned, which is like, is it the case that we can always find a closed form expression for like a thing like this, right? This is kind of what we had. We had G as L hat. And then we search for this, and this we called this W hat. But I'm just going to go back to like so we're going back to like optimization kind of basics. So forget about machine learning. We're going to learn some like simple things. Like we're going to learn about gradient descent, forgetting about machine learning, and then we'll port it back again to machine learning. So we're going back to like optimization world. So we have functions called g of W. We want to find their argmin, right? And the question is like, can we always find closed form expressions? And I guess in general, like maybe let me put that these things are vectors. Okay, maybe not, because we're going to start with the one-dimensional case. Okay, forget about that. So can we always find this, right? It would be great if the answer was yes, but the answer is unfortunately no. Okay, so the answer is no. Why could we find it in the machine learning case we had before? Well, it's because of the way we chose the loss function as a squared loss, and the way we chose the functions to be these really nice, simple linear functions. It turns out if you pick those functions to be neural networks, you're not going to be able to find a closed form solution, and then you actually need to do this kind of stuff. And we'll see when this happens in our course as well, and there's going to be some other benefits to it and stuff. But like, this is like the main motivation kind of. It's like, as soon as you make your function class anything more complicated than just these linear functions, you're really going to get stuck, and you're not going to be able to have a closed form solution for it. Okay, so the next, like, probably this and most of the next class is going to be playing around with functions and some examples and stuff like that. Okay, so here's the function example though. I already have it down here actually. So here's the function that right away gives you an example where there's no closed form solution, but it looks like a really simple function that you should be able to solve. So here's the function. It's just a squared function. And then I've added e of w, right? We've been playing around with w squared this whole time. Now I've just added e to the power of w. Look at this function. It like almost looks like w squared, except now it's just added with like the exponential function looks like this. So it's just been added that function. It's clearly convex. We're going to work this out in a second. But let's try to get its closed form solution. Okay. So first of all, let's check if it's convex. And the way we check if it's convex is we take its first derivative. We set that to 2 times w plus e of, the first derivative is this. And then the second derivative is equal to 2 plus e of w. Okay. Notice that this thing is always greater than 0. Right? So what this means is convex. Okay, visually we clearly saw it's convex. Great. So if it's convex, let's solve our problem. So, and like, of course here, okay, I'm assuming like we're looking at W in R, right? This thing's equal to the W space. So like we can do all these things that we talked about before, which is just take the derivative, set it to 0. And all this works. Like this mathematically, if you can do this, you get the answer. So let's do it. So you get e to the W equals 0. So we can try like rearranging, I don't know, maybe you get this, but like turns out there's no like closed form, there's no mathematical expression that gives you the answer to this equation. So what people say is there's like no closed form solution. Okay. So immediately we run into this problem already with something that looks very simple, and it's convex, and you'd think you could just find this minimum point, but it turns out you can't. Like in this way, you can't just like have some nice mathematical simple expression that tells you, okay, this is what at this W I get this minimum. Okay. So at this point, here's the motivation for this title here, which is that gradient descent will help us. Okay, and then maybe just machine learning, how it's solved. Like, remember, at the end of the day, in machine learning, the things we were talking about is not G's, but they're going to be loss functions. So this would be like, if you try to think, it's going to be a plot of the loss function, which has the predictor plugged in and so on, but like just a function. And what we end up in the situation is that sometimes there's no nice closed form solution to find the parameters for the like function we're trying to produce, like the one that the parameters that minimize the function. This would be like the parameters that minimize the expected loss, or sorry, the estimated loss. Okay, so now we get into some fun, because there's going to be a lot of plots and pictures and things like this. So let's do this. So we play around with gradient descent methods. And in particular, we're going to start with second order gradient descent to build some like intuition as to where this stuff comes from. And then we're going to actually always work with a simpler version of this called first order gradient descent. And that's what most of machine learning stuff uses. But we're going to start with the slightly more complicated version because it, like, I don't know, it's visually makes some sense of what's going on. So we have second order gradient descent. And this is actually usually called as like other things due to history stuff. Like you may have heard this, it's called like the Newton-Raphson, and I think that's how you spell it, method. Or like, I forget, maybe sometimes just the Newton method and so on. Okay. So what's the main idea here? The main idea is that we have this G of W. And for some, sometimes you'll have a G of W where like if you take its derivative, you can't solve for 0, right? But you might remember that if only G of W, right? If only G, like you might remember from like back in high school, like if G of W was like a second order polynomial, you had a quadratic formula to solve for like, okay, if it's a third order polynomial, you take the derivative, you get a second order polynomial. Then you use the quadratic formula, you have the solution, right? Turns out, if it was like a fourth order polynomial, then you take its derivative, right? You then get a third order polynomial, you set it to 0. Turns out there's a cubic formula, right? If it was a fifth order polynomial, you take its derivative, you get what? A fourth order polynomial. Set it to 0. There's a quartic formula. It looks much more complicated than the quadratic formula. But like these are just formulas that tell you the points at which it's equal to 0. And these are just like exactly mathematical expressions. This is like what we're looking for. Okay. Turns out, this is like some fun math facts, is that like there is no formula, right, for polynomials of degree 4 or higher. So like if you take a polynomial of degree 5 or higher. So if you take a polynomial of degree 5, you set it to 0. There's no closed form like mathematical expression that will give you that answer. And there's someone in like 1850 or something that proved that this can never exist. So for anything of degree 5 or higher, you can never find a solution that's like this nice closed form solution. Yeah, ever. So that's some fun math facts. So okay, so here's the math, the piece of information you should know, which is like if G of W is a degree 5 polynomial or less, then there exists a closed form solution for, and here we have g prime, which is the derivative, right? The derivative of g of w. So this gives us, if it's degree 5, you get its derivative, it becomes degree 4. There's a solution for g prime equal to 0. And this, if you remember, if this was like a second order polynomial, this is exactly the question you're trying to solve with the quadratic formula. Great. Okay, so what is our approach? So if only g of w had this form, so what do we do? So here's like maybe like our approach is, if we want the second order, like, or sorry, if we want this closed form solution, why don't we let's approximate. So let's approximate g of w, right, with a so we want to approximate something that's convex, so that, you know, the derivative actually, like when we set the derivative to 0, we actually get the minimizer. A convex and low order, and by low order I mean something that's degree 5 or less, right? A low order polynomial. Why? Because we can find its closed form solution. Okay? And in particular, in our case, since I said this is called second order gradient descent, in our case, we're going to choose a second order polynomial. Nice and simple, right? Second order, it's like x, it's like basically like a parabola that's a convex function. You can like visually see that. And so it kind of achieves all these goals. It's convex, it's low order, and there's a closed form solution. Okay, so that's the story. And like, but how do we approximate something with a polynomial? Well, I give you something called, that you might have learned in calculus before, which is like, okay, so in general, you use the Taylor series. Okay. So the Taylor series is a polynomial approximation to a function. I write it out for you explicitly. So the Taylor series, and you say it's a approximation at a point, okay? And I'll explain that in a second. So a polynomial approximation at a point, and that point we'll call W0, W0. And then we put the 0 at the top because it becomes, you'll see. Okay. So this is like, you would read this as like, it's like a Taylor series or a Taylor approximation of g of w at this point. And what is it? So the approximation looks as follows. Okay, this thing looks complicated, which is you basically take polynomials of degree 0 to infinity. And then it tells you what you should multiply each one of them by. And you should multiply by the nth derivative evaluated at W0 over n factorial times w minus W0 to the power of n. Okay, this thing looks kind of complicated. Good thing is we don't need this like infinite. So it turns out if you do this infinite thing, you actually get perfectly equal. Well, we don't need perfectly equal. We can get an approximation. So what we do is we use a second order approximation, right? And what this means is take the first three terms. Okay, so take the first three terms of the sum. That would be n equal to 0, n equal to 1, n equal to 2. So we have the approximation of degree 2, or order 2. What does that look like? This is much simpler. It looks like g of w is now approximately equal to our approximation. And we're going to call this approximation also g of w, but we're going to say it's an approximation using the Taylor thing at w0. Okay, so this like subscript w0 is going to indicate that it's a Taylor approximation and at the point w0. And we'll see a lot of plots momentarily about how all this stuff looks like. So this approximation, all I'm doing is expanding this sum. So yeah, the 0th derivative, well, that's just the function. And this is to the power of 0, so that's 1. So you get just the function times 1. Next thing, yeah, I just tell you all the terms. You can verify at home that this is actually the true thing. The first order term becomes this. Okay, and then the second order part is the second derivative, evaluated at W0 over 2 factorial, which is just 2, times W minus W naught squared. Okay, the point of the story is that we have an approximation of g of w, which is the following function. And the following function is a function of w. And look at where w shows up. We have a constant here. We just have w times something that's a constant, basically. And then we have w squared times something that's a constant. Just a second degree polynomial. Sure, you need to calculate these things, but you can do that. You just take the second derivative, plug in a number. Okay, let's go back to our example and see what does this approximation look like for the function we cared about to begin with. So I pull this guy up. So this is the function we were dealing with, right? Which was w squared plus e to the power of w. That was the black function we saw. Now, I need to choose a point, w naught. I chose 1. I don't know. I could have chose anything. I chose 1 because it's going to make the pictures look nicer when we move on and stuff. Pick any point. Yeah. So then I have this function, g of w naught. And if I plug it in, g1, whatever. It's the orange thing on the plot. So the orange thing, as you might suspect, the approximation is a quadratic function. Makes sense? It's a second order approximation. It's an approximation of w naught. This is this line here, w naught equal to 1. So at this point, it's actually a perfect approximation. And the thing to note is that at the point you approximate things, you get the perfect value. And then as you move away, so as I'm moving away from that value, you can see that these are getting quite farther and farther apart from the true value. So the squared thing is like, it's good until you move farther away. Great. Okay. So like, we want this point, but we don't have that function, or like we can't solve for it, but we have a function that looks like it. And we say it's an approximation, so what do? We solve for this point, right? Simple enough. And then like, okay, there's some error. Like this point is here, this point is here. We talk about this error in a second. So let's talk about exactly solving for this. So now, minimizing this function, which is our approximation function, right? Let's minimize the approximation. Let's find that point at the bottom of that orange plot. That's easy to do. So we need the derivative of this guy. So maybe I bring him down here. Okay, so we need to minimize this function. We know it's convex, it's a quadratic function. And so we minimize it. So let's calculate g prime of this approximation. Remember, this is a function of w. This is an important thing to note. This is just a number. There's no w here. This is a constant. This is the point we pick. This is just a number. So that for the derivative, that goes away. Now we look at this guy. We need to take the derivative of this. Well, that's just w times a constant. So the derivative is just g prime of, yeah, the actual function's derivative at w naught. Remember, this is like the truth. This is g prime is the actual function. These things are approximation. These are not the same g primes. Okay. And then we move on to here. Once again, in terms of w, okay, I'm not going to write out the explicit chain rule and stuff, but the story is the 2 moves out front, multiplies this term, and then you take the derivative of the inside, and that's just 1. Okay, so that equals, so the 2 is going to come out, right? It's going to multiply this 1 over 2, so that 2 goes away. And you get the following. Beautiful. So that's pretty simple. It's a function of w. The w only shows up here. And we need to set this thing equal to 0 if we want to find the minimizer. Let's solve this equation. So, okay, solving it. G double prime of w naught times w, right? That equals to g double prime of w naught times So it was multiplied by this, but then it moved to the right-hand side, so the minus went away. And then we have this. Okay, so finally this implies that our solution W is equal to W naught minus G prime over the second derivative. Okay, this is pretty simple, actually. So our solution to W is the following expression. You would just, you know W naught, that's the thing you pick. You can then calculate the derivative of G and G double prime, right? That was what we tried to do here. We have these things, G prime, G double prime, and then plug in W naught there. And then you get W, and supposedly that W is going to be this point. So let's see what happens within another example. Let's do it. Yeah. So this guy, I don't like, this plot is not as, it's missing one point. Okay. Yeah, I don't know why I have this plot. Let me just see. Okay, anyways, maybe we... Okay, let's use that plot, whatever. So yeah, we just need to solve for this thing. So I'm just gonna solve for, like, we knew what this thing was, like we seen it above. It turns out to be like 2 times x, or 2 times W naught, that's 2 times 1 plus e to the 1, okay? I don't know, that's some number. Then you get this double prime guy evaluated 1, so like, what am I doing? I just wanna calculate this thing, okay? Like, I just wanna calculate what this W is. We already have W naught, we picked it before, right? It was 1. Now I'm just calculating these two guys. We already have these, and I'm just plugging in 1 and 1. You can, if you scroll up like above, you see what the values are. This thing's 2 plus e to the 1. So now I can finally calculate what W is, okay? And I'm gonna call this W for some reason, and you'll see later. I'm gonna call W1 as the solution to this thing. And this thing is just W naught minus, okay. I plug in, maybe not. It's this thing, which is equal to what, right? This thing is equal to 1 minus this thing over this thing. That's just 1 as well, which equals to 0. So what we get is that this value over here is actually 0, as we see, and it's this minimum here. Okay, so this is a good place to end. So like, let me just 30 seconds to finish. Is like, what we did is we have this we had this G of W here. We have its approximation, this orange thing. And instead of finding this minimum, we found this minimum here. And we say, okay, if it's a good approximation, this is close to this. So maybe we can use that. And we're going to see how to improve on that in the next classes. But yeah. Okay, thank you.